Okay, inverse hyperbolic functions. Okay, written like this: inverse of sine x, inverse cos x, inverse tan x. Okay, similar to trigonometric functions. Okay, notice we can say r sine. Now in trigonometry we say arc sine. Okay, so the inverse of this function here we write as arc sine. Okay, notice that is r. There's a reason. There's a reason why that's arc and that's r. Maybe look it up. Okay, so the inverse of cos is written as arc cos. You see, it's r cos. Okay, and the inverse of tan is written like that, and that's arc tan. So the trigonometric inverses are arc sine cos tan. The hyperbolic are r. So there's a reason, an interesting reason. Why don't you look it up? Well, I'm not going to explain it in this video. Okay, but I'm just going to introduce some inverse hyperbolic functions for you. Okay, I've shown you already how you can use the calculator to work out the inverse sine of something. Okay, you can use that to solve some simple stuff. Okay, but what I'm going to introduce to you is how to get the formal definitions, because we can write that. So we can write sine, cos, and tan as exponential form. We can write these here as exact forms as well. Okay, maybe before I do that, just consider what the graphs look like. How to do it? Just pause the video and just consider it for a moment. Did you do that? Okay. Well, don't forget. Let's just do the first one, shall we? There's something important you've got to remember about this. Remember the Koch graph? Of course you remember that. That was the catenary. Okay. I've not drawn that well. I'll explain that in a minute. Okay. You might think, oh, that wasn't too bad. No, just because I want to do the inverse, you see, so I want to draw it a bit better. Yeah, that's, oh God, that's awful. Yeah, but yeah, there's a reason why I didn't want my first one. Okay, there we go. Remember the y-intercept 1, okay? So that's the Koch graph, okay? If you want to draw the inverse function graph, what do you got to do? Yeah, did you say reflect it to the line y equals x? Yeah, can you see why I redrew that? Because the first one was just painful. If you just rewind it, you'll see, because it didn't kind of look nice with the line y equals x. Okay. It was fine because I didn't scale the axes, so, but just, yeah, that looks better like that. Okay. Remember about inverse functions only exist for one-to-one functions. Okay. So these definitions in functions are really important, aren't they? Okay. So the inverse function only exists for a one-to-one function. That was not one-to-one, was it? Okay. So we've got to get rid of that bit to make it one-to-one. Okay. So what we'll do is we'll just reflect that to the line y equals x, and looks something like this. Okay, where the x-intercept there is 1. And that's the graph of y equals r cos x. I still prefer writing like that. Okay, so that's how you do that. Okay, maybe you had to go at the other ones. Okay, this is from earlier, of course. This is already one-to-one, so you don't have to restrict the domain or range. Okay, so you can reflect all of that through the line y equals x, and rather than get this shape, you're going to get this sort of shape, still pass through the origin. It will look something like that. Maybe you'll do it in decimals or something. Okay, and just see the difference. With this one, that is one-to-one, so you can keep the whole graph. Okay, the asymptotes, they get reflected, they'll become vertical. So you'll have an asymptote there, passes through -1, x equals 1. Okay, and rather do this, it'll do something like what it'll do. It'll do this, won't it? Okay. Yeah, and those are the graphs. That's kind of simple, isn't it? Okay. So let's get rid of that, okay, and let's talk about what I mentioned. That is the definitions of r sine, r cos, and r tan. Okay. Now, I can never remember these. I mean, there's so many things that would be nice to remember, to be honest, but you can't. You can't. Yeah. I'm not Euler. You know, he could remember everything. I can't. Yeah. Anyway, so the definition of r sine x is this, okay? Let me write it down. Oh, there it is. So natural log of x plus root x squared plus 1. And there are similar definitions for r cos and r tan. So why don't I write them down first, and then just prove one of them for you, okay? I can do the proof bit easily. So r cos, what's that going to be? Please hope it's now somewhere. Oh, there we go. So natural log. Is the natural log a bit obvious? I hope it is. Inverse of exponential e to the x. And they are inverse functions, aren't they? So quite similar. x plus root x squared minus 1, and then artanch is this, and that's 1/2. There's no way of remembering that. 1 plus x over 1 minus x. Okay. Now some of these are more clearly defined. For example, this you might say, that's kind of important. X is greater than or equal to 1. Okay. Why is that important? It's because of the square root, isn't it? Yeah. And then this one here, mod x is less than 1. Why is that important? Because of the denominator there. Okay. And when we do our natural log, and there's no complex numbers involved. Okay. So I just want to check I've written them down properly. Otherwise, it's going to be a little bit embarrassing. So all I'm doing is just copying down basically. Right, time to pause the video. How would you go about proving any of those? I'm going to do the top one. Okay, so maybe just try that. Okay, how do you prove that that equals that? Give yourself a couple of minutes. I'll check it's recording still. Hooray. Okay, so I'm going to do the top one. Okay, will I have enough space? Let's try. Okay, so what I'm going to say is I'm going to say y equals r shine x. And that sounds obvious, but it's really important. Okay, because it paves the way for doing the thing. Okay, now what I'm going to do is I'm going to write this. Shine y equals x. See that? Okay. Similar to trigonometry, of course. I'm just going to do the shine of both sides. So shine y, and the shine of that, it undoes the r shine, doesn't it? Okay. So we've got shine y equals x. Okay. Now what am I going to do? Okay. I'm going to write x as 1/2 e to the y subtract e to the negative y. Maybe you're thinking, oh yes, it's kind of obvious. Well, pause the video, maybe, and just have another go at it and see if you can do something from there. Okay. What's our objective here? Okay. What is our objective? Okay. I want to make y the subject, basically. So I'm not sure why I swapped the sides around. I want to make y the subject. So I'm going to write 2x equals e to the y minus e to the negative y. Okay. And you might think, how are you supposed to do that? It's like solving an equation, like trying to find what y is. Okay. We had one of these in the previous video. Multiply both sides by e to the y. So 2x e to the y is equal to e to the 2y, subtract 1, and then put everything to one side, e to the 2y, subtract 2x e to the y, subtract 1 equals 0. Do you recognise what sort of equation we've got? It's a quadratic. Okay. Let's solve that quadratic. Okay, so e to the y subtract x squared. I said you to before, don't like quadratic formula with these at this stage. Complete the squares quicker and neater with the solutions as well. Okay, so expand that bracket. Okay, we'll get e to the 2y subtract 2x e to the y, which is that, plus x squared. We don't want the plus x squared, so complete the square by subtracting x squared. Okay, so that bit is the same as that, and then subtract 1 equals 0. Yeah, I was right. I'm not got enough board space on my. Never mind. Right, down here again then. So I'm going to write e to the y minus x squared is equal to x squared plus 1. Can you see how this is going to turn into that now? You could probably play the last few steps in your head, can't you? Okay. Yeah. We're going to square root both sides, aren't we? Yeah, we're going to square root both sides. Okay. Remember what I said in the previous video about the plus or minus? Yeah, you want the positive square root. Notice it's positive square root. Okay. Do you remember why you want positive square root? Let's just put it in, shall we? So positive square root. Okay. I'll answer that question again in a minute, okay? And then what I'm going to do is I'm going to add the x to both sides, like square root to both sides now, so I've just got that, haven't I? Okay. Then I'm going to have e to the y is equal to x plus that. Yeah, so e to the y is equal to x plus that. And I'm hoping the last stage is obvious, y equals natural log of that, which is this. Okay. Right, suppose you had the plus or minus. Let's consider this case. X squared plus 1 is greater than x when you square root it. Yeah. this term is greater than that term. X subtract a large number gives you a negative value. You don't have the natural log of a negative value. That's a simple way of explaining why you don't have the plus or minus. Okay, but the real reason really is because it's a one-to-one function, so you can't have plus or minus. Maybe, as a special treat to you, you try and work out what this is. Yeah, that's what special treats are for mathematicians, isn't it? Okay, exactly the same process. Okay, it's kind of rewarding when you do it. So I'm not going to do it. I'm going to let you do it. Okay, so y equals r cos x, similar sort of thing. Okay, this one's just a bit of a pain. It's still doable. Maybe you do that as well. Okay, because it's kind of it's helpful. Okay. But they're really nice, okay, and I want to end the video on this point, okay. What I really like about hyperbolic functions is they're more versatile. What I mean by that is you can write what sine, cos, tan are in terms of exponentials. You can write them another way. You can write the inverses as natural log expressions. You can't do that with arcsine. Okay, if you want to work out arcsine a number, there's no other formal way of defining it, okay? And that's what makes these really, really nice, I think, okay? I hope you enjoyed that.